André, Roberto, Paulo, and also everyone who helped to organize this meeting. This is a joint work with Eileen, André, and Danielle. We work with the numerical approximations of equations which have non-local terms. So in the beginning, I'm going to present a few words I'm going to say a few words about the model, about the mathematical model. Consider the very simple approach, which is the linear hyperbolic model, no dispersion, no nonlinearity, just to introduce, to review the von Neumann stability analysis, extend this analysis to the linear dispersive equation. That's the equation we are mostly interested in. And later, by the end of the talk, share some ideas about the Hilbert, spectral properties of the Hilbert transform approximation by the alternate trapezoidal rule. This is also a joint work with Aline. She's a graduate student now at the LNCC, Petropolis. So our model will come, our equation will come from these strongly nonlinear dispersive equations. This is an internal wave model where you have two layers, and the unknowns are the displacement of the internal layer plus a depth average horizontal part of the velocity field on the upper layer. And the key elements in this equation for us will be this Hilbert transform on the strip of width H2 over L, so the depth of the lower layer divided by the wavelength, and also this dispersion parameter beta, which is related to the thickness of the upper layer. So we are going to drop the nonlinear terms. So the equation reduced to that equation, where you have only this local term. That's the only interesting term that remains. We drop the interesting term as well. We will consider also beta equals to 0. We consider the plane wave equation, just to review the von Neumann equations, von Neumann analysis. And just for a little motivation, let us start with an ugly picture. So if we simulate the plane wave equation and use a high current number, we're going to experience some instability, numerical instability. And this instability goes away as we introduce dispersion. So for the same current number, the simulation goes smoothly, no problem with numerical instabilities. And we want to understand why. What is the exact relation between this beta here, this dispersion parameter, and the maximum allowed, let's say, CFL ratio. That's what we want to understand. So as I said, let us begin with the very simple case, the plane wave equation with periodic boundary conditions. I'm going to discretize first in space. Let's do let's say that school trick of going from PGE to ODE, and then from ODE to algebra. So let's go first to PGE to ODE. Our spatial derivatives will be written as a matrix vector product, where our knowns now are written as vectors where we sample the unknowns over the grid points of, for simplicity, a uniform grid. That's how the matrix looks like. It's a typeless matrix, so constant along diagonals, circulant due to periodicity. And we're going to consider schemes which yield a skew-symmetric matrices. That's the one we're going to study. And schemes such as the fourth order finite difference that Eileen used 2 days ago. So that's how the matrix look like for this scheme, for this fourth order scheme in space. To do von Neumann for this problem, I'm going to transform to frequency space. So we use the discrete Fourier transform. We introduce this normalized frequency index. Can also think this as k delta x, kh, which is more common in other is more common in the over the literature. This DFT can be written in vector form, so we introduce a Fourier matrix involving these exponentials here. Just to point out that the indices for the transformed vectors have this shift by n over 2. So the main quantity we want to transform to the Fourier transform are products of the discrete derivatives, let's call like this, by some vector. And if we do some algebra, this product on the physical space turn into this kind of similarity product on the DFT space. And luckily, this thing here will be diagonal. The Fourier matrix diagonalizes the derivative matrix that we saw with this circle and stoiplets and so on. So things get simpler for this kind of matrices. We can write these eigenvalues with the aid of an auxiliary function that is pretty much normalized. For example, for our finite difference scheme in space, that's how this function looks like. A simple combination of trigonometric functions. And once the discretization in space is done, we move to discretize in time, and that's when Runge-Kutta takes place. At least that's the method we're studying in particular. If we condense all these several equations that build up the Runge-Kutta into just two equations, we have this system of two equations that look like a little like a Taylor series truncation. That's a nice form to analyze. And to study these equations, we're going to move to DFT space, and now we have a lot of products to take care of. And all these products will become in discrete space as just products of the eigenvalues or powers of these eigenvalues. So things get simple. We want to study the stability of some special modes. So we introduce a solution, particular solution of this in this fashion. So a amplification factor that will grow with n times the initial perturbation. And we plug this expression into this equation, we arrive in a eigenvalue problem, which this is a 2-by-2 problem that we can easily solve. And we find this amplification factor. So that will give us information about stability. But also for free, we have information about dispersion. If we choose, still in particular, plane wave solutions, transform them to Fourier space, we can relate this quantity to our amplification factor. So we can easily compute phase and group velocity from these quantities. In particular, phase velocity is the one we're going to see in the pictures. So that's the analysis for the finite difference in space and Runge-Kutta in time. That's how the amplification factor behaves, like the absolute value of amplification and the phase velocity. And here increasing the current number. Ideally for simulations, we want to use the time step as large as possible. So we want to reach the limit, this limit. And the question is how to find this limit, how to find this threshold, not by MATLAB, but analytically. So we found out that this is possible to find precisely an expression for this optimal, let's say, this optimal current number this number will be square root of h, 2 over 2 times square root of 2, divided by the maximum value of the auxiliary function that we use to define the eigenvalues. So this stability is in the sense that the amplification factor does not grow over 1. This absolute value does not grow over 1. So that's what I mean by stability, by being stable. So what we want to do is to take the absolute value of this quantity here. So this is a complex number, a complex function, let's say. Taking the absolute value, so we have real part, imaginary part. We can split this in the definition of absolute value, taking this square, and then do a little exercise of algebra, and we arrive into a nice 8th degree polynomial with 1 plus this polynomial here that has a 0 multiplicity 6 plus this plus minus root of 8. And this gives us this bound for this quantity, nu times gamma. So we just now need to find the inequality for the current number. In particular, for our finite difference, we find that nice number 206. Just to remind you, in the beginning, we have a simulation where this current number was 215, and the oscillations start to show up. Okay, so that was the easy equation. Now we go to the a little more complicated problem, the linear dispersive. And just a few words on the numerical approximation of the Hilbert transform. We do in, let's say, spectral-wise approximation. We start with the Fourier series representation of the Hilbert transform plus this derivative in x that comes from the linear model. So that's how the exact, let's say, Fourier series looks like. We want to discretize this. So the first thing we have in mind in the discretization is to get rid of these infinities. So that's what we do first. We truncate the series up and down. Next, we discretize this Fourier coefficients as well by DFT, and evaluate this function over the grid points. And when you do this, our Fourier matrix comes in. So this expression can be written in matrix form very nicely by this Fourier matrix times this diagonal that has kind of the symbol of the Hilbert transform. And if you want to take GFT of this, it would be quite simple. The matrix F is orthogonal. We can easily find the DFT just having this diagonal multiplying the vector U. This derivative here, perhaps, it introduces a I times.
The sine k times k. So you're just missing the absolute value.
There's no sine k. It's actually because it's a Hilbert-like transform.
Oh, it's a Hilbert-like transform.
It's not the Hilbert transform.
Right. As soon as you say Hilbert transform,
It's there. It's not on the strip. Mm-hmm.
Plus, what I mean is that there's also the derivative built in.
That's Thanks. So back to our linear dispersive model. So I want to pack all those coefficients into a single coefficient beta, but keeping having this delta, this lower thickness over L, over wavelength outside. This will help us for the analysis. Discretize all of this. That matrix I just mentioned will appear here. And just as the linear hyperbolic, this matrix, it will be easily written, will be easily diagonalized with the aid of the Fourier matrix. So that's how it looked like, where those eigenvalues are related to this to these constants that we have here, from the, let's say, from the symbol. Okay, now the game is the same game as before. We want to write the full discretization. Now we want to couple this system with the discretization in time with Runge-Kutta. Write in the Fourier space, diagonalize everything, and we have this new amplification factor where the function gamma now has this term that comes from the dispersion. One thing to notice in this term, comparing with the original terms from the standard wave equation, is now that we have, let's say, a free k here on this expression. We cannot express this as like number of grid points per wavelength or some quantity, some normalized quantity, as we usually do. So we have to introduce here the space increment as well. So the analysis must take into account, let's say, the number of grid points per wavelength plus the time space or the wavelength, perhaps, or the k. No wavelength, but frequency. So just one picture on this. We have here the dispersive amplification factor, the absolute value of the amplification factor for the dispersive model against the standard wave equation, against the hyperbolic amplification phase velocity. And here we see the gain in dispersion, in stability of the dispersive model. That was the 215 I used in the beginning. And in general, we have a general result as well in which this gain of stability will be explicitly be dependent on beta. So that's how it will appear. The argument is pretty much the same as before. We're going to find in the end we're going to find that 6-degree polynomial, and we find this inequality now for gamma tilde. And the only thing we have to do is to make an estimate over the denominator that goes now as numerator of that expression. We take this minimum of k delta, hyperbolic cotangent of k delta. That's why I left the delta here. And this have as minimum 1. And we find this expression. And the thing to look here is that this number, being greater than 1, will give us a higher tolerance for the current number. Just as an example, let us imagine that this normalized beta, this normalized dispersion parameter is 3. We would have here root of 4, 2, so we could use twice the time increment if we have such a large dispersion, just to give an idea. Okay, now just this extra material about this is still ongoing work on the computing the Hilbert type transform, but now not using spectral, not using the Fourier series, but trying to use approximation on physical space. We are considering the alternate trapezoidal rule. And if we discretize this integral, this singular integral here by the alternate trapezoidal, this k, this kernel, we still have to consider what is the appropriate kernel in this problem. We haven't thought of this yet. But the discretization is very well known, at least by the alternate trapezoidal rule. We have this parameter epsilon that jumps that rules out all pairs kj when their difference is 0, 2, 4, and so on. So we have this, the grid points are jumped by this method. Still, they have the high accuracy. And if we write this approximation, this discretization, as a matrix vector product, we have a matrix with all filled with zeros, and the zeros go along diagonal every 2 diagonals. And we want to analyze how does eigenvalues look like, how the spectrum of this thing looks like. So to analyze spectrum, we want to find eigenvalues. We want to take, for instance, either one row or one column. Let's take one column of this matrix and find the GFT of this column. That would give us the eigenvalues. In particular, let us use the FFT algorithm. The first step of FFT, we split the problem in two problems, two FFTs of size n over 2, where we take the odd components and the even components of the initial vector, the initial data. But these numbers, the odd components are all 0. So we have 1, 3, 5, and so on. They are 0. So all of these will go away. So x prime is 0, y prime will be 0 as well. And our FFT will be much simpler. We have only the 2 prime term, and we have a little gain in this form. We have mostly exactly the same expression on both equations, just a change of sign. So in particular, those two one is the opposite of the other. But there are other relations between the yj, the jth eigenvalue, and some others eigenvalues in the spectrum. We have this relation between 4 possibly different eigenvalues. So this guy, the conjugate, minus him, minus the conjugate. So we have orbits of 4, 8, 12 eigenvalues, everyone with the same absolute value on the complex plane. So then what happens? Let us think in the case where our kernel is either an odd function or an even function or an odd function. For an odd function, the matrix will be symmetric. So all eigenvalues will be over the real axis, whereas the skew symmetric in the even odd functions, the matrix will be skew symmetric. Everyone goes to the imaginary axis. So all these eigenvalues will be collapsed over either the real or the imaginary. So many of them will coincide. Most of them will coincide. So we have, beforehand, we have a double multiplicity guaranteed. So that's what this picture will, that's what we're going to see in the picture. So we take one example where we have a singular kernel, the second derivative of the cotangent, where we can compute the eigenvalues exactly. And let us compare exact eigenvectors with, they are in red, with the ones found by the alternate trapezoidal method. And we see that they all come in pairs. This problem keeps on if we refine the mesh, so they will follow us, at least in the standard implementation, regardless of mesh refinement. We always have this issue of double multiplicity of eigenvalues. Okay, so that was what I want to present. So we have this study on the numerical stability of schemes for the linear dispersive equation. We hope that this will be a first step for going on harder equations, the equations that are more like the ones that are of interest of waves in fluids. We try to explain this extra stability of the linear dispersive case. And now in progress, we're trying to understand more about the Hilbert transform on physical space on the using this alternate trapezoidal, and later move on to study other more complex problems. So that's our work so far, and thank you for your attention.